back. In this video, we're going to be discussing stochastic and regular stochastic matrices. So this is going to build on concepts that we previously studied in matrix algebra. And there's going to be a lot of vocabulary in this video, so it's important that you understand the terms and just get practice using the words correctly. So if you're following along in the text, this is going to be on page 233. This is where this lesson is going to come from. Okay, so first off, we're going to have to define a probability vector. So a probability vector is a vector that is non-negative and sums to 1. So it is non-negative and the entries sum to 1. Okay, so I'll explain the second point first, since I think it's perhaps easier to understand. So, in other words, if you have a matrix, a vector like this, you notice that the sum of the values goes to 1, right? So a quarter is a half, and a half plus 1/2 is 1. So you have 1/2 plus a quarter plus a quarter, and this sums to 1. When we say that the vector is non-negative, what we mean is none of these entries here are negative. So 0 is okay. We don't want to say positive because we want to include the possibility that an entry is 0. So for example, even though this matrix sums to 1, because 1 plus negative 1/2 plus 1/2, the 1/2s are going to cancel and you just get 1. Yes, this does sum to 1, however, this value is not non-negative, it's negative. Okay, so let's see, okay. So something that we can note is that if you have a probability vector, you can essentially represent the final entry as 1 minus the previous entries. So for example, a probability vector with 3 entries, right? With 3 entries can be represented as x, y, and 1 minus x minus y, where x and y are greater than or equal to 0. Okay, and the sum of them is, well, let's just check. So if we add these together, right, what is this? Well, we don't know what x and y are, but when we add these values up, the x and the y's cancel, and so this is just equal to 1. So this representation is going to turn out to be very helpful for setting up equations that we need to solve. Okay, the next concept we need to discuss is what a stochastic matrix is. So a stochastic matrix, this is a matrix whose rows are probability vectors. So a matrix whose rows are all probability vectors. So Okay, so we don't need the columns to be probability vectors, but we need the rows to be probability vectors. So some important facts that are a result of this definition is that because a probability vector has non-negative entries, every entry in a stochastic matrix is going to be non-negative. Okay, so if you have a vector or a matrix that is not a probability vector or a stochastic matrix, you can, in general, transform them by an appropriate multiplier. Well, certainly in the case of vectors, sometimes in the case of the matrices. So let's do an example real quick. So suppose you had a vector v with values 1, 2, 3. Okay, so the idea is we want to create a vector w, and w is going to be equal to av, where a is a number, okay, right? So that the sum of the values of w sums to 1, okay? So let's see. How about I multiply everything by a, and so right, because effectively what this says is that w is going to be a1, a2, and a3, right? Because I'm multiplying vector v by a, and we want these values to sum to 1. So this is going to look like a plus 2a plus 3a is equal to 1. So that's 6a is equal to 1. So a is equal to 1 over 6. So the vector that relates, or that, let's say, rescales v, this is going to be 1/6, 2 over 6, and 3 over 6. Okay, and we're going to simplify that. So this will be 1/3, and this will be 1/2. Okay, so this is the probability vector that points in the same direction as v. It points in the same direction because anytime you multiply a vector by a positive number, it's going to maintain the direction but change the length of it. And you can review the older videos on this concept if that is confusing. Okay, so let's do a quick example of a probability matrix, sorry, a stochastic matrix. So a stochastic matrix example would be matrix A with, let's say, 1/2, 1/2, 3/4, and 1/4, right? Why? Well, because 1/2, 1/2, this is a probability vector, and 3/4, 1/4 is another probability vector. Okay, so I think it's worth saying really quick, we haven't discussed probability theory yet in this course, and you might be a little thrown off by this mention of probabilities. However, don't let the word scare you. It means exactly what I just told you. The sum of the values is going to sum to 1, and each of those values is greater than or equal to 0. Okay, so the next concept we're going to discuss is regularity. So a stochastic matrix is regular if there exists some power of it such that all entries of that matrix are strictly positive. Okay, so a stochastic matrix is regular So I'm going to say a stochastic matrix P is regular if P to the n has all positive entries for some n. Okay, so let me stress, this time when I say positive, I mean positive in the strict sense. So in other words, it's not enough that a value is equal to 0, it has to be greater than 0. Okay, so what is this power in? What does this mean? Let's do a quick example. So if we have a equals 0, 1, 1/2, and 1/2, this is going to be, well, first off, is it a stochastic matrix? Because notice that the only matrices we care to talk about regularity of are stochastic matrices. So the first question is it stochastic? Are all the entries non-negative? Yes, they are. Although this value here is 0, that is okay because we're not asking if a to the first power has positive entries. We're asking if a to some value is going to have all positive entries. So first thing is it stochastic? Yes, because all the values are non-negative, okay? And if you look at each row, the sum of the values is equal to 1. 0 and 1 is 1, 1/2 and 1/2 is 1. Therefore, because all the values are non-negative and the rows sum their values to 1, this matrix is a stochastic matrix. So it is a stochastic matrix. Okay, so now we're going to check if it is a regular matrix. So you might be able to look at the matrix, and if you're very familiar with matrix algebra, you can often just tell if it is a stochastic matrix. Sorry, if it is a regular matrix. But for us, we're just going to take powers. Okay, we're just going to take powers. So let's look at a squared. So a squared, this is literally just a times a, right? Okay, so if you don't remember how to do matrix multiplication, go back and review these concepts. So I'm going to go pretty quickly over this. 0 and 0 is 0. 1 and 1/2 is 1/2. 0 and 1 is 1. 1 and 1/2 is 1/2. 1/2 and 0 is 0. 1/2 and 1/2 is a quarter. And 1/2 and 1 is 1/2, and 1/2 and 1/2 is a quarter. So this entry is going to be 1/2 and 1/4, or 3/4. Okay, so this is a squared. So by our definition, right, this is for some n. So in this case, n is equal to 2, and that works, right? If we look at this, right, it is, and here's a quick comment I want to make. I guess I forgot to make it. The product of any pair of stochastic matrices is still going to be a stochastic matrix. So I believe that's an exercise in the book. We may have it on the homework. I haven't decided yet. But if you look at this matrix, it is just A times A, right? And A is a stochastic matrix, so it is the product of stochastic matrices, namely A and A, and therefore it is also stochastic. And indeed, we see that the values are non-negative and the rows sum to 1. In this case, also, all the values are strictly greater than 0, and so now we can say affirmatively that A is regular. Now, indeed, A squared is also regular because A squared raised to the first power, right, is, well, it's just equal to this, and all those values are positive, and so yeah, so a squared is also regular, but the thing that we're really interested in is a regular, and it is regular because a squared satisfies the conditions. Okay, so the next concept we're going to cover is that of fixed points. Fixed points. So a fixed point is a non-zero vector v, right? So v is a fixed point if it is non-zero and, well, we should say fixed point of, right? We should say it's a fixed point of A if it is non-zero and v of A equals v. Okay, so what do I mean by non-zero? I literally just mean that if we look at the entries of v, right, let's say it was v1, v2, and v3, then at least one of these is not equal to 0, right? So there's only one zero matrix, or zero vector, and it looks like this, right? 0, 0, 0. At least in the case of vectors with length 3, right? Length 3. Okay, so for example,